What's going on, guys? Alan. We're going to do this one more time, talking about unit circles and these new type things we're going to mention as circular functions. Still going to be a lot of the same, but just a new format. So hope you're ready, because here we go. So as I mentioned in this section, it's going to be a lot of familiarity, at least there should be. But now we're going to be talking, instead of reference angles that we've been dealing with a lot, we're going to convert them to what are called reference arcs. And so obviously we're going to have to know the difference between the two. And so instead of using our typical angle for theta to represent any angle that we know or don't know, we're going to now use a different symbol to represent the arc. And we've already talked about an arc length, and we used the letter S. So you may have had a hunch already that that's what we're going to actually use in order to talk about these trig functions in a little bit different form. And we're going to continue on with this radian angle measurement that we're finding hopefully more useful, and because of that fact, very, very important. So even though we're talking about the same trig functions with the same angles, namely the 30, the 45, the 60, and even the quadrantal multiples of 90, in any of our four quadrants, now we're going to be continuing on with the radian measurements, but now as arc lengths. All right, so we're going to start with this unit circle here. And if you remember, in the unit circle, we were given this equation, x squared plus y squared equals 1, in order to draw it. So that gave us these four quadrantal angles that all had a radius length of 1. And so remember, we talked about that the arc length was equal to r times theta. And if we are saying that we are on what is called the unit circle, given a name because of our radius of a length of unit 1, then we can say that this new formula for an arc length is equal to theta, which, remember, this had to be in radians. That was the key to that. So therefore we know that the angle theta in radians is equivalent to that of our arc length. So if we wanted to write sine of theta in radians, we could say that that is therefore equivalent to the sine of S. And that, my friends, is the big difference in this section from the ones that we've previously worked on. Now remember, theta represents an angle, where S represents an arc length. But because we know that they are equivalent, then we can basically put in either or. Okay? So in this section, that's what we're going to be dealing with. Still working with the same trig functions in the same way, just having a different look on our unit circle and using that arc length of S opposed to just theta for our angle. So then how could we write our big three and then their reciprocal functions in this format? Well, like we said, we could definitely write this as sine of S, cosine of S, or tangent of S. But what did all of those equal? Well, remember, just like before, we had sine is equal to y over r, cosine was x over r, and tangent was y over x. None of that changes other than the fact that we are now on the unit circle. And because it's the unit circle, that means our radius is length of 1. So we can actually say that the sine of S on the unit circle is simply and only equal to y. Cosine, our x. And of course, hopefully you remember that tangent was equal to the sine over the cosine, which is therefore y over x still. Okay, so a little bit nicer in the fact that we can take one less thing out of the equation, no pun intended, because our r, radius length, is now equal to 1. And that's the easiest circle that we could possibly deal with, so that's why we like to go over that in the most detail and use it if we have a choice. So for the other ones, then we know it would just be 1 over y, 1 over x, and still x over y. When dealing with the unit circle and our new found angle measurement, we're going to call the arc length S, denoting that we are on the unit circle. Okay, so not a whole lot new, actually some newer nice things that we can then get rid of the radius length being different and always say that it's a length of 1 on the unit circle. And so for us, we're going to continue on with all the things that we've talked about in the past, but now in this new format using the unit circle. So when I go to evaluate at some given point that they're going to give me, say this one right here, which I know is some x comma y, well, if it's on the unit circle, which should be pretty obvious that it is, because they're giving us all 4 of our quadrants being a length of 1 comma 0, 0 comma 1, and so on and so forth, all a length of 1, meaning our radius is 1 because of that equation, x squared plus y squared equals 1, which is the equation of a circle centered at 0, radius of 1. So in order to get to that point right there, I know that it's always going to be some x over and some y up. But if we know that the radius is 1, then just like we said all along that the sine of any angle is equal to y over r, well then if I took the opposite over the hypotenuse, that would be equal to that y value over that radius of 1, which we said would be that. So again, if we wanted to rewrite it in terms of its arc length, because we know that those are indeed equivalent, then we can also say that this is just equal to y. And if that's equal to y, then we could do the same for cosine, which we said would therefore be equal to x. So rather than writing any point as x comma y, we can write any point on this circle as cosine of our arc or angle S, and then sine of that arc or angle. So now these are equivalent and an alternative way to write an ordered pair point x comma y. All right, so still dealing with that, and again I wanted to rehash and make sure that you all remember that all students take calculus to know which things are positive and which are negative, because again it would all have to deal with the direction of these things. So there it is in a nice confined form for you for your notes if you wanted to write any of that down. And again, notice one more time, I mentioned it before, but I'll do it again, that we do have restrictions with the trig functions that are not simply sine or cosine. All the other ones could possibly have something in their denominator that is not a radius and therefore could possibly be a 0. Right? So we got to be careful when those things are undefined, so that when we get to graphing these and also evaluating them, then we know when we could have issues. So the last thing I want to talk about is this unit circle, in that what if we looked at just the values that we've been talking a lot about, those reference angles, the 30s, the 45s, the 60s, and even our quadrantal angles. Could you give me the ordered pair that we just reviewed here that our x is equivalent to and that our y is equivalent to. Could you give me those values? Have you memorized them yet for every single one of these quadrants? Because if I want all 4 quadrants, say I wanted the 45, or I wanted to know the 60, for example, as well, then what would each one of those be in quadrant 2, or quadrant 3, or quadrant 4? So hopefully, like I mentioned, you have already memorized these values for the sine, cosine, and tangent of 30, 45, and 60, because not that you have to memorize this, but here's another nice way to memorize it. It's very, very simple, so let me go over it with you. But before I do, go ahead and pause it and see if you can fill out as much of this as you can. All right, so just to remind you that the one I told you to definitely memorize was the sine of 30 degrees. And that should be equal to 1/2. Which then means I also know that the cosine of 60, the complement to that, would also be equal to 1/2. And if I know that, then I also should know that the sine of 60 or the cosine of 30 would also be equivalent to the other 30, 60, 90 value that we dealt with a lot, and that's √3/2. And then lastly, the sine and cosine of 45 degrees would be equal to √2/2. The one that has √2 has the 2 angles that are the same. The one that has the 30, 60, 90 has the √3 in it. So the only one that we'd also have to deal with is obviously tangent. But the cool thing is I don't need tangent in this if I know sine and cosine. And of course, remember we just reviewed that x comma y is equivalent to cosine of our angle comma sine of our angle. So if we have all of these values, then we're good. And if you notice that there's only 1, 2, 3 different values that we really need to memorize for this entire unit circle. So for the first one here, the sine of 30 we know is 1/2, and the cosine of 30 is the √3/2. Which, since I know 30 is the complement to 60, then I can just reverse these here. The cosine of 60 is 1/2, and the sine of 60 is √3/2. Now the easiest one is the one that they share the same, and those are the 45s. That's easy. They're both √2/2. And remember, those all stem from the 30, 60, 90 special right triangle and the 45, 45, 90. So with this, all I have to know is all the other quadrants, which remember, all students take calculus to see what's positive and what's negative, or you should already know that from the center point, this direction, all my x's should be negative. And that goes for both quadrants. But then up here, the y value should be positive, but down here, the y values should also be negative. Right? And then in quadrant 4, still the x is now going to be positive, but y would be the only thing that's negative here. And if I know that the 30-degree angle were these two values, then I also know that they're going to have to be that with this 30-degree angle, which is a reference angle, and this 30-degree angle as a reference angle. And lastly, this one. All of those are my 30-degree reference angles, which means for sine and cosine, they will have those exact same values as well. So I will have the √3/2, comma 1/2, √3/2, comma 1/2. The only thing that will change are the signs. for each of those. So now looking at the 45, we know that the 45-degree angle would be that one right in the middle in all four of our quadrants. And from there, super easy, we know that they're all, the x and the y, the cosine and the sine, going to be root 2 over 2. And then lastly, the 60-degree reference angle, which for us would be right here at 120. Because remember, we're always referencing the x-axis, 240, 300. Those would be all of our 60-degree reference angles, which if you notice, looks like it's over about 1/2, and then up more than 1/2 to be root 3 over 2. So what we're going to do is list all of those same values, 1/2 and root 3 over 2 for our x and our y. Again, the only thing that would be different would be where they are positive and negative. And that, my friends, is the unit circle. Again, called the unit circle because what we're dealing with is a radius of 1, which is why 1, 0 would be at the 0, 0, 1 at the 90, negative 1, 0 at the 180 or pi, and 270 or 3 pi over 2, 0, negative 1, and then that 360 or 2 pi back to our 1, 0. All right, so if you want to take the time to memorize this, great. If not, all you really need to know are the reference angles. And if you have these right here, you pretty much have everything you need to build and find any of the other 4 trig functions. So one thing I wanted to mention to you at this point in time, I'm not going to get into too much detail with it right now, is if you notice that the x values were between 1 and negative 1 on our unit circle. So you can see our x values on this unit circle goes from this 1 value all the way over to everything in between, but to negative 1. So when we're talking about the x value, remember now we're talking about our cosine function. So the cosine's range, the range of values that come out when evaluating it, would be somewhere between negative 1 and 1, including those values. And likewise, if we were to talk about the y value, which is sine, then it too would go between 1 and negative 1 and every value in between as we rotated around. You can see my y value would start at 0, get a little bit bigger, all the way until it got to 1. Then it would start to get smaller again, still positive values because it's above the x-axis, but all the way back to 0. And then we would start becoming larger y values from the x-axis, but negative this time because it's down below, all the way until we got to a negative 1. And then they would start getting smaller again, my y values would, but still below the x-axis, so negative, until it got back to 0. Right? So what can we plug in? That's the difference between the domain, all right, and the range is what we can get out. The range of numbers that come out from the domain, what we can plug in. All right, so the sine and cosine, you can see there are no restrictions. We can plug in any value we want. But for the others, tangent and secant are paired up. Again, that is because, remember, sine and cosine at any point in time would be y over r and x over r. And so since our r can never be 0, that's why we have no issues. But for tangent and secant, remember, tangent of any arc or angle is equal to y over x. And secant, which is the reciprocal function to cosine, is r over x. So notice they both have issues at x when x is 0. And when would x not be left or right any? Well, that would be when we're up or down on our quadrantal axes of 90 degrees or pi over 2 or 270 degrees and 3 pi over 2. So that's why we have issues at any odd 1 pi over 2, 3 pi over 2, or keep going around 5 pi over 2, 7 pi over 2, 9 pi over 2, or even negative 1 pi over 2, 3 pi over 2, any odd pi over 2. And the way we can always guarantee an odd number is make it even by multiplying it by 2 and then adding or subtracting 1. So that's what they mean by 2n plus 1. That's any odd pi over 2. And similarly, when we talk about the cotangent and cosecant functions, cotangent is just the reciprocal function of tangent. So now that's x over y. And cosecant, the reciprocal function of sine, which is r over y. So now you can see the issues in the denominator that we cannot have equal 0 is where y is equal to 0. And where y is equal to 0 would mean we're not up or down any, so we would be right or left at our quadrantal angles of 0 or pi. So this time it's any number of pi. That means we're here at 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, or again in the negative direction as well. Right? So we'll talk more about that in the next chapter, but I wanted to start laying that foundation since we are talking about the unit circle and all of its values and attributes. So that's it for this section. Not a whole lot that's new, just a few little nuances, talking about our angles being arcs instead, but still being able to apply our reference angles of 30, 45, and 60 in any quadrant. Except now we're going to call them arcs, denoting that we are on the unit circle.